So, orbital potential energy, or why it's so honkin' expensive to put stuff in space. Potential energy. Up until now, we've been saying potential energy is equal to mgh. But as Gabby just pointed out, little g, the gravitational field, changes as you go cosmic. So what we're going to say today is, okay, Megan, for the beginning of the year when you were on the Earth, use potential energy equals mgh. But as soon as you start going cosmic, we're going to need something new. We're going to start off with a bit of recall. Recall the area under a force versus distance graph. What was the area under a force versus distance graph? It was work. It was work. In fact, if I call this F, if I call this D, and I stick some kind of a line like that, let's call that right there point A. Let's call that right there point B in our lovely little sketch. That area there, in fact, it isn't just work. If I wanted to be even more specific, it's the work required to move from A to B. From location A, wherever it is, to location B, wherever it is. And if we were, like in the work unit, always on level ground, then we also said if that's how much work it took to get from point A to point B and your potential energy didn't change, then all of that work ended up being a change in kinetic. When we put stuff in outer space, is its height going to be changing? Okay, we're going to need to revise this a little bit. For a graph of gravitational force, so I just did a generic force versus distance graph. What if I graph gravitational force versus a very specific distance versus the separation distance from the center of the planet, of the black hole, of the whatever? What would that look like? Well, let's put FG on the y-axis. Let's put R on the x-axis. Who's in Math 12? Okay. Don't write this down, but for what it's worth, it's going to look an awful lot like that because force is proportional to 1 over the radius squared. So to give you an idea of what this graph is going to look like, what does y equals x squared look like? This one you all know. What's that a graph of? Parabola. You guys have done reciprocal functions in Math 12, those that are in Math 12. It's going to be the reciprocal of a parabola. For those of you that don't know that, don't freak out. You don't need to know that. I'm going to tell you, though, it's going to look something. That's what an inverse square graph looks like. That's what the reciprocal of a parabola looks like. I don't care about scale. It's roughly that shape, though. Okay. Oh, you can also see that when your distance is 0 and you have infinite mass, it shoots off to infinity. There's your black hole. Those that are in calculus, there is a limit and an asymptote there. Consider. Let's get specific. Here's gravity. Here's R. Here's our gravitational force graph. We're going to put a point right here. I'm going to call it radius of the Earth, right there. Radius of the planet, radius of the surface of whatever you're starting out on. We're going to put a point right here. We're going to call it radius of orbit. If I were to calculate that area that's the work required to lift an object from the Earth's surface to a height of, or a radius of, our orb, to an orbital radius. Here's the problem. We don't have an equation for the area of a curvy shape. This was one of the reasons Sir Isaac Newton invented the calculus. Who's in calc? You guys are just doing, or just in the process of doing derivatives, and you've learned how you can use that to find the slope of a curve. In the final third of the course, somewhere around the end of April, beginning of May, you'll learn that you can also do the opposite of a derivative, and if you do the opposite of a derivative, that actually tells you the area underneath the curve. So instead of moving the exponent down to the front and subtracting 1 from the exponent in your power rule, if you take the coefficient, add 1 to the exponent, and divide by the new coefficient, you'll find you reverse the procedure, and it's tougher, but it's called the integral, fancy word. You'll find that tells you the area underneath the curve. But none of you are in calculus, I have to assume. So here's my bad math workaround that gets us to the right place. Since work equals force times distance, we can say work equals gravity times radius. That's still force times distance. Work equals big G, big M, little m over r squared times r. Oh! What do you notice? What cancels, Megan? Okay, there's going to be an r that cancels. Kind of cool. This is going to give us our equation. Draw a big box here. Instead of calling this work, we're going to call this potential energy. Leave a space. But the equation for potential energy is big G, big M, little m over r. It's identical to force, except instead of an r squared on the bottom, what do you have? Just an r. Oh, but you got one more thing, Taylor. It's negative. It's negative. That's the formula that's on your formula sheet. It's negative. And I wrote here, why negative? Well, who's in calculus? It's negative because when you take the integral of the force equation, you end up with a negative sign in front. Okay. Sadly, I can't use that explanation. Why is it negative? Well, look at my tennis ball here. When I lift it up, I give it potential energy. And the reason you know it has potential energy is when I let it go, what happens? It wants to fall. It wants to fall. If I lift it higher, it has more potential energy. Yes? It wants to fall even more. Supposing I lifted it all the way out to the edge of the universe. It would not want to fall because there's no gravity acting on it. If it doesn't want to fall, how much potential energy must it have if it doesn't want to fall? As a number. Zero. Zero. If you go to the edge of the universe and you let this tennis ball go, it'll happily float there for all eternity. Doesn't want to fall, which means it has zero potential energy. But to get it there, I would have to pour in energy. I would have to do work, which means starting on Earth, I have less potential energy. I add potential energy to get to the edge of the universe. And how much potential energy do I have out at the edge of the universe? So if I'm adding energy, if I'm starting out with less potential energy than 0, what numbers are less than 0? Negatives. Negatives. The reason it's negative is we have defined 0 to be relative to infinity. Out at infinity, you have no potential energy. If you're closer than infinity, you have less potential energy than infinity. And since we define 0 to be out there, what's less than 0? Negative. The magic phrase we say is relative to 0 at infinity. So I wrote here, why negative? Out at infinity, at the edge of the universe, an object would have 0 potential energy because it's not being affected by any gravitational field. It doesn't want to fall anywhere. If our height is less than infinity, we must have less potential energy than out at infinity. What numbers are less than 0 potential energy? Negatives. So the phrase that we say is relative to 0 at infinity, potential energy is negative, big G, big M, little m, over R. Ready? Prepare for a fair bit of number crunching. Example 1. How much work is done in lifting a 1,200 kilogram satellite from the surface of the Earth to a height of 1.2 times 10 to the 7th meters? Okay, height is important. They didn't give me the radius, they gave me the height. I'm going to have to add the radius of the Earth to that because they've just told me how high above the Earth. I'm going to have to include that in. What's this question asking me to find, Chelsea? Work. Okay. Work is change in potential plus change in kinetic. Can't use force times distance because gravitational force changes as you go higher. So since the force is not constant, I've got to fall back on the work energy theorem. Oh, and there's clearly no graph. The other key word here is we're lifting. I phrased this question very, very carefully. What we're doing is we're lifting it up there with imaginary crane or angels or whatever you want to say, but it's not in orbit. As soon as you let it go, it's going to come crashing back down. Because it's not in orbit, how much kinetic energy does it have? None. Because to put it in orbit, we said last day, I'd have to give it a whole bunch of kinetic energy, just the right kinetic energy, just the right orbital speed, so that it's falling at the curvature of the Earth. So we're starting out saying, just to get it there and not put it in orbit, how much work? Oh, and we're assuming we're starting out with the initial kinetic energy of 0, which technically isn't right, but in our magic physics world, it's going to be, and I'll explain why in a bit. Well, what's changing anything? Okay, so this is going to be now, in grade 11, or earlier this year, you would have said, potential energy, MGH. Are we going cosmic now? I can't use MGH. Why? Because G is going to be changing. I have to use my new potential energy equation. Work is going to be, I already wrote the potential energy final minus initial. Negative big G, big M, little m over R final, because it's the radius that's changing, not the masses. Minus negative big G, big M, little m over our initial. There's our new equation. Oh, what do you notice in the middle there? Little minus minus is going to become a plus. That's nice. This is going to be negative big G, 6.67 times 10 to the negative 11. Big M, Earth, little m, doesn't cancel, 1,200 divided by the final distance from the center of the Earth. Well, the final distance from the center of the Earth is going to be the radius of the Earth plus the altitude that you are above the Earth at. Now you'll have to read the questions carefully. Sometimes they'll give you the height above the Earth. Sometimes they will just give you the radius from the center of the Earth, which is less work. What'd you say the middle is? Don't reach for your calculator yet, Diana. What'd you say the middle is? Trust me. What's the minus minus? Plus. And then it's going to be 6.67 times 10 to the negative 11. Don't go for your calculators yet. 5.98 times 10 to the 24th. I got some tricks I want to show you. 1200 divided by our initial radius. We're starting from the surface of the Earth. Surface of the Earth has a radius of 6.38 times 10 to the 6th. Here's how, and now pick up your calculators. This is how I recommend you do this. We're going to be clever. You'll notice a lot of these numbers appear twice in both expressions. We're going to try and exploit that on our good calculators, especially if you got a graphing one. You'll really like this, but here's what I would do. Clear, clear, clear. Negative 6.67, scientific notation button, negative 11, times 5.98, scientific notation button, 24, times 1200, divided by bracket 6.38, scientific notation button 6, plus 1.2, scientific notation button 7. And I'm going to zoom out and double check. I want to make sure I get the first expression right. I'm only going to do the first expression right now. So negative 6.67 times 10 to the negative 11, check. 5.98 times 10 to the 24th, check. Times 1200, check. Divided by radius of the Earth, check. And height, check. My final potential energy, you get negative 2.60, and because I'm going to use this, I'm going to go to like 5 or 6 sig figs until I'm done. So I'm going to go to negative 2.6041. That looks pretty good. Negative 2.6041 times 10 to the 10th. Plus, and this is where I'm going to get clever. Hopefully you all have a calculator that lets you just backspace. On the graphing calculators, it's second function enter. On most scientific calculators, it's back arrow or up arrow. Because all I'm going to do is navigate to this negative, delete it. I'm going to navigate to the plus sign after the 6.38 times 10 to the 6th, and I'm going to go delete, 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 delete. It's less typing, but also, Jason, less room for error, for typos. Enter. And I get 7.5022. How about, yeah, 7.5022. Times 10 to the 10th. Yes? I want to add that to negative 2.6041 times 10 to the 10th. You know, isn't that just the same as subtracting? So Megan, what I'm going to do, because I have this number stored, I'm just going to hit my minus button. 2.6041 scientific notation. That's how you can get this with the minimum amount of typing, but more importantly, Mabad, with the minimum amount of keystrokes to make stupid errors on. How much energy does it take to lift it up there? That much. You know what? I think 4.90 when I round off, times 10 to the 10th joules. Now, we haven't even put it in orbit yet. All we've done is get it up there. Oh, and this is way too low. We're ignoring air resistance. We're ignoring all our magic physics that makes the math yucky. We're ignoring all that. So this is minimum. This is why when they did the moon rockets, they built them in 3 stages, because as soon as you've burned the fuel and you've used that engine, now it's just dead weight. Why would you want to spend rocket fuel? Because where does this energy come from, by the way? It comes from the rocket fuel. Why would you want to spend rocket fuel increasing the potential energy of useless mass? Ditch it. Three-stage rocket was the best way to go. Now, this is not an orbit tie. As soon as you let this go, it's going to come rocketing back down to the Earth, going faster and faster. Might even burn up in orbit. I'd have to see crunch the numbers and see how much heat was generated. But certainly, it would be hitting the ground with some tremendous speed. What if we want to put it in orbit? Well, then I want to give it some kinetic energy, too. Then I don't want to cross out that KE that it is at the top of the page. Like this one. Example 2. Did I give you a whole page to do this one question? Yeah? And you know what, Megan? I'm still going to say write small. This is about the longest question you'll do all year. Let's read. It says, how much work, work, is done placing a 925 kilogram, I forgot the word satellite, in orbit? You know what? That's the difference between the previous question and this one. We're putting it in orbit with an orbital radius. Oh, they gave me the radius, not the altitude. So that's kind of nice. Of 2.6 times 10 to the 7th meters. What was your question?
Is that radius?
That one, if they say radius, that includes the, that's from the center of the Earth. So I don't need to add the Earth's radius to that. Thanks. Nice. This time, none of these is 0. We're going to find the change in potential, which is going to take just as long as it did before. We'll put a lovely box around that answer. We're going to find the change in kinetic, which is going to take a few lines. We'll put a lovely box around that answer. And then the work is going to be add the two answers in the box together. We're going to put a triumphant box around that answer, because that's going to take us a while. What do you want to find first? Change in potential or change in kinetic? Doesn't matter. Which one? Change in potential? The one we just did? Okay. I'll change colors so it stands out a little bit. Change in potential is final minus initial. Josh, can I just use MGH, or are we cosmic here? We are cosmic here. So it's going to be negative big G, big M, little m over R final minus negative big G, big M, little m over R initial. The change in potential energy negative 6.67 times 10 to the negative 11 big M. Are we Earth? Since it doesn't say a different planet, let's assume we're the Earth. 5.98 times 10 to the 24th. Satellite is 925 divided by 2.6 times 10 to the 7th. We don't need to add the radius of the Earth because it specifically told us this was the orbital radius. It didn't say altitude or height. Hey, what's a minus minus the same as, John? Mr. Dueck? Yes, Ty. I noticed that in that second expression, the whole top is the same as in the first expression. Yeah. Okay. If you want to. You can put 3 ditto marks for 3 variables if you're feeling particularly lazy. I won't freak out, because we're going to do that on our calculator anyways. Right? We're going to reuse it twice. What's our initial? Oh, starting out on the surface of the Earth, which was 6.38 times 10 to the 6th. Try this on your calculator. I'm going to freeze the screen and get an answer. And if you can't get this on your calculator, now is your chance to ask. In fact, I'm going to cheat. I'm going to go to my Block B lesson and just yoink it from there, because I can. thereby thoroughly irritating the people that are following me. And I even tried to show you what I typed in on my calculator. Is that right? No, you guys are still going. Sorry. Yep. One down. That's what my last class got, but some of them aren't too smart, so maybe. .364 times 10 to the 10th joules. Terry, that's what it takes to get you up there. But if that's all you crunch, this is coming crashing back down because you haven't given it any sideways tangent speed. You haven't given it any kinetic energy. So there's the change in potential. Let's find the change in kinetic. That's going to be final minus initial. Here's where we're going to do a little bit of bad physics to keep the math nice. We're going to assume initial is 0. That you're starting at rest. This is only true if you're taking off at the North or South Pole. But if you're anywhere else on the Earth, because the Earth itself is rotating, you have the kinetic energy that the Earth has given you. In fact, the closer you are to the equator, the faster you're rotating, the more initial kinetic energy you have. You can use the Earth to slingshot you. This is why Cape Canaveral was built in Florida, in the southernmost portions of the U.S. The closer you are to the equator, the better. And this is why they launch out east. They take the speed of the Earth with them. Best place to launch would be right on the equator. But there's not too many industrially developed nations with the infrastructure to do that right on the equator. They are talking about building an ocean platform that can actually sail the seas, and they could sail it to the equator or close to it and launch. But the problem is, if you're on the ocean, you've got waves. You don't want to be going, okay, launch now! It adds other infrastructure issues. But there's designs out to try and look at that. This, by the way, was one of the big challenges for the Russian space program. Does Russian have southern nice locales to launch from? Nope, or yet. So they had to brute force it because they couldn't take advantage of the Earth's kinetic energy the same way the US did. They built their rockets bigger. That's why the Soyuz rocket, the one that the Russians currently use, is the biggest, most powerful rocket ever designed. The Russian solution was, we'll out-engineer Earth. We can do it. The Russian space program also had some other issues. One of the other reasons the U.S. launched from Florida is you launch over the ocean in case something goes horribly wrong, but also you have a nice splashdown area for recovery. Again, the Russians didn't have access to a year-round thawed ocean. So the Russian space capsules landed on the ground. They didn't splash down in water. And on at least 2 occasions, the parachutes did not open. And the cosmonauts had about 3 minutes to converse with each other as they were falling to their certain death, knowing they were going to die. I don't know who's lost more astronauts, whether the Russians have lost more cosmonauts or the U.S. has lost more astronauts. The U.S. has lost 7 and 7 and 3, so 14 and 3. The U.S. has lost 17. I'm not sure if the Russians have lost more or less. I think did I mention this? This is the week anniversary of all 3 of the U.S.'s space disasters. So when Apollo 1 burst into flame on the launch platform and basically incinerated the 3 astronauts that were inside during the practice run. That was this week in 1968. When the Space Shuttle Challenger exploded in 1986, that was this week. And when the Columbia broke up over Texas, that was this week in 2002 or 2003. I've said it before. How many space shuttles were built? 6. How many blew up? 2. 1 out of 3. Traveling to space is incredibly dangerous and incredibly difficult. Having said that, we got a Canadian up there right now. In fact, I think, any of you have Twitter accounts? Yeah, it's worth subscribing to Chris Hadfield. He's putting out some spectacular photos and some good tweets. He signed off last night, and then about a half an hour later, whoops, not signing off, fire alarm went off. They had a fire alarm on the space station. Thankfully, it was a faulty sensor, false alarm. I'm willing to bet that those sensors are designed to be so sensitive that you'd rather have 50 false alarms than ever miss. Like, you probably want it to go off almost before the spark even thinks about occurring, right? So anyways, I'm sure it's a fairly regular occurrence, but I'm sure it was also an adrenaline rush. So that was a long ramble to say, we're going to pretend the kinetic energy is 0 to keep the math nice. Yo.
My mom's biology teacher was supposed to go on that building in the movies.
Really?
Yeah, he was in Saskatchewan. He was supposed to go and something went wrong. And then after,
So he's part of the training for that.
Yeah.
Because there was a teacher on the one that in 1986, it was Christy McAuliffe. And she was going to be doing the first ever lesson from space. And so in 1986, I was in high school, but all over the U.S., elementary and high school students were gathered around the TV to watch the launch. And so it was a traumatic event. You had all these little kids cheering for this teacher that was going up into space, and then seeing the explosion and hearing the command that they give is lock the doors. Whenever NASA gives that command, they hate giving that command. When they say lock the doors, what they're saying is we're locking the doors and no one is leaving until we find out what went so horribly wrong.
Yeah.
Been issued only a few times in NASA's history. Yeah.
He was noticing after he
Yep.
left.
Yeah. No, it was a traumatic event. Let's go on to more pleasant things and talk about the future. No, you know, it's space travel's tough, but you know, often science comes with risk. Discovery comes with risk. I think it's also, though, part of what makes it kind of nerdily cool too. So I think we're going to end up with this: a half mv squared. I was going to write v final squared, but really I think what we're talking about is v orbit squared. Do I know the mass of the satellite? Yeah, because that's little m. It's 925, not the mass of the Earth. Do I know the orbital speed? Jaron says no. But Jaron, you know what? From last day. You know what? I'll use the one with the V in it because we want orbital speed. From last day. Oh, you know what? From last day. And then we said that gives us V squared. How do you get the V by itself? Wait. You know what? I was going to get the V squared and square root, but then I said, maybe I actually just want to leave it as a V squared, don't I? Why square root when I can just leave it as a V squared and plug what? Big G, big M over R is apparently what you can replace the V squared with. Let's do that. That's less work. I'll take that. So the change in kinetic energy is going to be a half little m, big G, big M over R, which R, I think R final, R orbit. Yes? Now, those of you that are particularly observant might notice, hey, Mr. Duick, we can rewrite this. Instead of putting little m in front, what if you put it on the end? And what you have is the equation for potential energy, but positive. It turns out that if you want to find out how much kinetic energy you need to put something in orbit, it's the same as the potential energy, but positive, and half of it. Kind of cool. I mean, yes. In fact, when I do them, you know what? I'm going to leave a 1/2 in front right now so that I know it's a half mv. I kind of want to reinforce the half mv squared kind of dealy. But now on my next line, when I start crunching the numbers, yeah, I'm going to go like this. Ready? Let's plug and chug. Change in kinetic is going to be 6.67 times 10 to the negative 11. Big M, mass of the Earth. Little m, what was the satellite? 925, I think. Divided by, yeah, Dorothy, I'm just going to go 2 times 6.38 times 10 to the 6th. The other reason is, I think if you just, again, backspace on your calculator, you've got the whole top typed in again. You might have to go second function, enter second. You might have to backspace a couple of calculations, but I think you got the whole top typed in again. And then you can just replace the bottom with a, in fact, I think, for me, I actually had this line. All I had to do was insert it 2 times. Yeah. I got really lazy, by the way. I put the times 2 on the very, very end. I said, it doesn't have to be at the front. Why don't I put it after? It's even less typing. Come on. You can't beat that. What'd you get for the kinetic energy? Let me go find it. There it was from last class. Is that right? Oh, you know what? I made a mistake. I used the radius of the Earth here. It's not the radius of the Earth. I even said radius of orbit, didn't I? So, I'm sorry. Caught myself. Orbital radius, not radius of the Earth, which was 2.6 times 10 to the 7th. Yes? Sorry, folks. Orbital radius. You know what? I'm going to do this in my notes just to reinforce that. There, I'll put an orb on the R to remind myself. Do it. Don't do that again. And I think when you do that, you get 7095212,500. 1, 2, 3, 4, 5, 6, 7, 8, 9. 7.0952 times 10 to the 9th joules. That's how much kinetic energy. Oh, and where does that kinetic energy come from? The rocket fuel. Oh, and remember, to get the satellite to that speed, you've got to get the whole rocket and its mass also to that speed so that you can gently let the satellite go. This is why it is really more efficient. Instead of having, like the space shuttle was a very inefficient way to bring stuff up there. Best way to do it is stick the satellite on the very, very tip of a small disposable rocket that's going to fall off the satellite and fall back down to the Earth and burn up in the atmosphere. Best way to do it. Not necessarily most environmentally friendly. I'm not talking about that. I'm just saying in terms of efficiency for energy purposes, it's the way to go. It also, you'll notice the little mass doesn't cancel. The bigger your satellite, the more energy it takes. The amount of potential energy it took to get that new Mars probe, the Curiosity, which weighs well over a ton, well over 1,000 kilograms, all the way out to Mars. Ooh. How far apart are Mars and the Earth? A fair chunk. So how much energy? A fair chunk. A lot. We're not done. Oh, you know what, though? I will put a little box around that answer in pride. And I put a box around that one. Final answer. Work equals 4.364 times 10 to the 10th plus 7.0952 times 10 to the 9th equals 5.07. Now I'll go to 3 sig figs. 5.07 times 10 to the 10th joules. That's a fair chunk of energy. Hey, if you're bored, look up the mass of the space shuttle. Put the space shuttle's mass in there, which I humbly suggest is considerably larger than 925 kilograms. Wow! Is that why they had the huge fuel tank on the... Oh, is that why the booster engines fell off? And yes, all of that. Example 3. A missile is launched from the surface of the Earth. Its fuel is used in an initial burst, and so as it rises, the only force it experiences is gravity. So this time, we're not going to have initial kinetic be 0. We're going to say you flip the switch, and in our thought experiment here, Alicia, instantly you're at full speed, and then we shut off the engine, and you coast. What happens to its kinetic and to its orbital potential energy? What happens to its kinetic energy as it leaves the Earth? As you launch something and throw it up, what happens to its speed? Decreases. So what happens to its kinetic energy? If the kinetic energy is a half mv squared, and you just told me the v is getting smaller, so we would say no, no, yes, yes. So the answer is either C or D. What happens to its orbital potential energy? C. In fact, what's happening is if you, on the Earth, were able to fire your rocket and instantly get to speed and then shut off your engine, all of your kinetic would slowly turn into potential. In fact, if you knew how much kinetic energy you had, you could even figure out how high you could get. And this leads to the next question. How much kinetic energy would you need? What velocity would you need so that you could fire your engines on the Earth once, shut them off, and escape the Earth's gravitational pull? What we call escape velocity. Come back to that. The questions you're capable of doing right now. Number 1. Number 2. Number 3. So 1, 2, 3. 4. I'm going to assign 7. I haven't really talked about 7 yet. This is a conservation of energy question where you know how much potential you have at the top and it starts to fall down. You can calculate how much potential you have at the bottom. Where did that potential go? It went into kinetic. How much kinetic? How much speed? See if you can try number 7. Number 8, 10, 11, and 13. Some videos to show you here.